My dear students, welcome back to our channel. In this video, I will be explaining the MCA second semester subject Machine Learning as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 1 first important short question is: define machine learning, ML, and its importance in data-driven decision-making. Machine learning, ML, and its importance. Machine learning, ML, is a branch of artificial intelligence, AI, where computers are trained to learn from data and make decisions without being directly programmed for every step. Instead of writing fixed rules, we give a machine lots of examples, data, and it learns to find patterns and predict outcomes. Why ML is important in data-driven decision-making? In today's world, huge amounts of data are generated every second. ML helps in analyzing this data quickly and accurately. It makes smart decisions automatically, saving time and effort. Example: e-commerce sites like Amazon suggest products based on your browsing and purchase history using ML. Banks use ML to detect fraudulent transactions by spotting unusual patterns. ML is essential because it turns raw data into actionable insights. It helps businesses, doctors, and engineers predict trends, solve problems, and improve services, making decision-making faster, smarter, and more reliable. Next important short question is: to write the difference between maximum likelihood, ML, and maximum a posteriori, MAP, estimates. Difference between maximum likelihood, ML, and maximum a posteriori, MAP, estimates. Both ML and MAP are methods to estimate unknown parameters in machine learning, but they differ in how they use information. Feature maximum likelihood, ML, maximum a posteriori, MAP. Definition finds parameter values that maximize the likelihood of observed data. Finds parameter values that maximize the posterior probability, uses both data and prior knowledge. Focus relies only on data. Uses data plus prior beliefs. Formula theta ML is equal to argmax P, data theta. Use case best when we trust data completely. Best when we have extra knowledge about the parameter. Example: suppose you are guessing the fairness of a coin. ML estimate probability of heads only from the coin toss data. MAP use toss data plus your belief. Example: most coins are fair, to adjust the estimate. In short, ML is equal to data only, MAP is equal to data plus prior knowledge. Next important short question is: 3. Define conjugate priors in Bayesian learning. Conjugate priors in Bayesian learning. In Bayesian learning, we use probabilities to update our beliefs about a parameter after seeing data. A conjugate prior is a special type of prior distribution that makes this updating process easy. If the prior and the posterior, updated belief after seeing data, belong to the same family of probability distributions, the prior is called a conjugate prior. This is helpful because it simplifies calculations, as we don't have to switch to a new type of distribution every time we update. Example: if we are estimating the probability of getting heads in a coin toss, use a beta distribution as the prior belief about the probability of heads. After observing data, number of heads and tails, the posterior is also a beta distribution. This makes updates quick and easy. Key point: conjugate priors are chosen for mathematical convenience, so Bayesian updating is straightforward. Next important short question is: 4. Define prior and posterior probabilities in Bayesian learning. Prior and posterior probabilities in Bayesian learning. In Bayesian learning, probabilities are used to represent our belief about something before and after seeing data. Prior probability, P, theta. This is your initial belief or assumption about a parameter, theta, before looking at any data. Example, if you think a coin is fair, your prior belief is 50% heads and 50% tails. Posterior probability, T, theta vertical bar data. This is your updated belief after observing data. It is calculated using Bayes' theorem. Posterior is equal to likelihood times prior evidence. Example, if you toss the coin 10 times and see 7 heads, your belief changes and the posterior may say the coin is slightly biased toward heads. Key point. Prior is equal to belief before data. Posterior is equal to updated belief after data. This process helps make better predictions based on evidence. Next important short question is 5. What is the role of likelihood in Bayesian estimation? Role of likelihood in Bayesian estimation. In Bayesian estimation, the likelihood measures how well a certain assumption, model or parameter value explains the observed data. It shows how likely the data is given a parameter, theta. Mathematically, likelihood is equal to P, data theta. It is used in Bayes' theorem. Posterior likelihood times prior. Here, the likelihood updates the prior belief to form the posterior belief. Example. Suppose you believe a coin is fair, prior, 50% heads. You toss it 10 times and get 8 heads. Likelihood tells us how probable it is to get 8 heads if the coin is fair. If this probability is low, your belief updates, posterior, and you might think the coin is biased. Key point. Likelihood connects observed data to your belief about the model, making predictions more accurate. Next Unit 1. Top 5 long questions. First important long question is 1. Explain probability concepts, random variables, PDF, CDF, conditional probability, Bayes' theorem, used in ML. Probability concepts in machine learning. Probability helps us deal with uncertainty in machine learning ML. It allows algorithms to make predictions based on data patterns rather than fixed rules. Let's break down key concepts. Random variables. A random variable is a variable whose value is uncertain but follows a probability. Example, tossing a coin. Let x is equal to 1 for heads, 0 for tails. X can take 0 or 1 based on probability. Probability density function, PDF. For continuous variables, PDF shows the likelihood of a value occurring. Example, height of students in a class, PDF forms a smooth curve where taller or shorter heights are less common. Cumulative distribution function, CDF. CDF gives the probability of a variable being less than or equal to a value. Example. Probability a student's height is less than or equal to 160 centimeters. Conditional probability. Probability of an event a happening given B already happened. P AB is equal to P AB, P B. Example, probability of rain today given cloudy weather. Bayes' theorem. Bayes' theorem updates beliefs based on new data. P HD is equal to P DH, P H, P D. Example, medical test says you have a disease. Bayes helps calculate true chance based on prior disease rates and test accuracy. Why important in ML? Used in algorithms like naive Bayes, Bayesian networks, hidden Markov models. Helps in classification, predictions, and decision-making. Quick Python example. From SYMPY import symbols. P underscore H, P underscore D underscore given underscore H, P underscore D is equal to 0.01, 0.99, 0.05. P underscore H underscore given underscore D is equal to P underscore D underscore given underscore H asterisk P underscore H, P underscore D. Print P underscore H underscore given underscore D, hash posterior probability. Memory tip. Think of PDF as shape, CDF as area under curve, conditional as filtering events, and Bayes as updating beliefs. Next important long question is 2. Describe key linear algebra concepts, vectors, matrices, eigenvalues, eigenvectors, with examples for ML applications. Key linear algebra concepts for machine learning. Linear algebra is the language of machine learning. It helps store, process, and transform data easily. Vectors. A vector is a list of numbers that represents a quantity with both magnitude and direction. Example, a student's marks in math, science, English V is equal to 85, 90, 75. In ML, vectors represent data points or features of a dataset. Use each row in a dataset is often a vector. Matrices. A matrix is a rectangular grid of numbers arranged in rows and columns. A is equal to 1 to 3, 4. Example, a dataset with 3 students and 3 subjects is a 3 times 3 matrix. In ML, used for storing datasets, transformations, and neural network weights. Use matrix multiplication is key for training ML models. Eigenvalues. An eigenvalue shows how much a vector stretches or shrinks after a transformation. Example. In image compression, eigenvalues tell us which features are important and which can be ignored. Use helps reduce dimensions in large datasets, PCA. Eigenvectors. An eigenvector is a direction that doesn't change during a transformation, only scaled by its eigenvalue. Of is equal to lambda v. Example, in facial recognition, eigenvectors identify key face features. Use simplifies high-dimensional data. Machine learning applications. Vectors represent individual data points. Matrices store large datasets and weights in models. Eigenvalues eigenvectors used in PCA, principal component analysis, to reduce dataset size while keeping important features. Quick Python example. Import numpy as np. A is equal to np.array 2, 0, 0, 3. Values, vectors is equal to np.linang.ag a. Print eigenvalues, values. Print eigenvectors \n vectors. Memory tip. Think of vector a single arrow, data point. Matrix a table of numbers, dataset. Eigenvalue size of stretch. Eigenvector direction of stretch. Next important long question is 3. Discuss convex optimization and its role in training ML models. Convex optimization and its role in ML. What is convex optimization? Convex optimization is a branch of mathematics that focuses on minimizing or maximizing a function where 1. The function is convex, shaped like a ball, meaning any line between 2 points on the curve lies above or on the curve. 2. The feasible region, possible solutions, is also convex like a smooth, round shape without holes or sharp edges. A convex function guarantees a single global minimum, best solution, which is easier and faster to find. Example. Imagine finding the lowest point in a ball. If the ball is smooth, convex, you can confidently say, this is the lowest point. But if it has multiple dips, non-convex, finding the true lowest point is harder. In ML, this is like finding the best parameters, weights, for a model. Role in machine learning. 1. Model training. Most ML models, like linear regression, logistic regression, and SVM, use convex optimization to minimize a loss function error. Example, linear regression minimizes the mean squared error, MSE, which is a convex function. 2. Faster convergence. Since convex problems have a global minimum, optimization algorithms, like gradient descent, converge quickly and reliably. 3. Regularization. Convex optimization helps apply techniques like L1L to regularization, preventing overfitting by keeping weights small. 4. Scalability. Convex optimization scales well to handle large datasets and high-dimensional data, which is common in ML. Memory tip. Think. Convex is equal to ball shape. Optimization is equal to finding the bottom of the ball, best solution. ML connection. Training a model is equal to finding weights at the bottom of this ball. Mini Python example. Import numpy as np. Hash convex function f kiss smiley is equal to x2. X is equal to np dot linspace minus 5, 5, 100. F is equal to x asterisk asterisk to hash ball-shaped curve. This function has a single minimum at x is equal to 0. That's why convex optimization makes ML training easier, faster, and more reliable. Next important long question is 4. Explain Bayesian learning in detail with ML and map estimates and examples. Bayesian learning in detail with ML and map estimates. What is Bayesian learning? Bayesian learning is a probabilistic approach to machine learning that updates our beliefs about a model as new data comes in. It is based on Bayes' theorem. Posterior is equal to likelihood times prior evidence. Prior, what we believe before seeing data. Likelihood, how likely the observed data is under a model. Posterior, updated belief after seeing the data. This helps us handle uncertainty and make predictions based on both prior knowledge and data. Example. Imagine predicting if it will rain tomorrow. Prior, you know September is monsoon season, high chance of rain. Data, today's weather is cloudy. Posterior, combining both, you conclude there's a high chance of rain. ML versus map estimates. 1. Maximum likelihood, ML, estimate. Focuses only on data and ignores prior belief. It chooses parameters that make the observed data most likely. Example, fitting a line, linear regression, by minimizing error. 2. Maximum a posteriori, map, estimate. Considers both prior knowledge and data. Helps when data is limited or noisy. Example, predicting disease chances using medical history, prior, and test results, data. Why Bayesian learning is useful in ML. Deals well with uncertainty, real-world data is noisy. Works great for online learning, updating model as new data arrives. Useful in spam detection, medical predictions, and recommendation systems. Key difference to remember. Concept uses prior. When to use. ML estimate no large, clean datasets. Map estimate yes small or noisy datasets. Memory tip. Think of ML as data-only learning and map as data plus prior belief. Bayesian learning is like a student updating their guess about exam questions after hearing hints from a teacher and seeing past papers. Next important long question is 5. Write a detailed note on statistical decision theory and its applications in ML. Statistical decision theory and its applications in ML. What is statistical decision theory? Statistical decision theory is a framework for making decisions under uncertainty using probability and statistics. In simple words, it helps us choose the best decision or prediction based on available data, possible outcomes, and the cost of making wrong decisions. It combines 1. Probability, how likely each outcome is. 2. Loss-cost function, the penalty for wrong predictions. 3. Decision rule, a strategy to choose the option that minimizes risk or cost. Example. Imagine a doctor predicting if a patient has a disease. If they predict no disease but the patient is sick, the cost is very high, wrong decision. If they predict disease and the patient is healthy, the cost is lower, unnecessary test. Statistical decision theory helps choose the prediction with minimum total risk. Key terms. Term meaning example. Hypothesis assumption about data patient is sick. Action decision taken give treatment. Loss function cost of wrong decision misdiagnosis cost. Risk expected loss average cost over many predictions. Applications in machine learning. 1. Classification problems. Helps in choosing the class label that minimizes error. Example, email spam detection, false spam marking versus missing spam. 2. Regression problems. Minimizes prediction error using loss functions like mean squared error. 3. Medical diagnosis. Balances risk between false positives and false negatives. 4. Self-driving cars. Makes safe decisions, stop, slow down, by minimizing risk of accidents. 5. Finance and fraud detection. Detects fraud while minimizing false alarms. Memory tip. Think of it like playing safe with numbers. You predict based on probability, but also think about loss if you are wrong. It's like a chess player planning moves to minimize risk while maximizing chances of winning.